Welcome to today's video. Today we will be speaking about merge sort. Let's go. Before we get into the merge sort algorithm, we'll have to understand what is merging. Merging is the process of combining two sorted lists into one list, and the list can be of different sizes. Alright, for example, we have A, we have B, right? And we let the index be A, the index of A be I, and the index of B be J, the index of C be K. Alright, so we check which value is less between the first indexes, and it's 2. We insert this one. Then we move the element down, we move the index down, and it will become 8 being compared to 5. And 5 is the smallest one, and 5 will be the second element. It goes on and on, right? To merge the two lists, A and B, we compare the values of the index I of A and the index J of B. We copy the smallest one of their index and we'll move the index downwards. If the two lists are sorted, the results will also be sorted. And the time complexity for merging is theta m plus m. We let this one be n, the elements here be m, and the elements here be n. Alright, so here's a pseudocode for merging. It's basically what I've explained here. The function here, we initialize the merged array, it's empty. We initialize I, we initialize J for the second array, and then we check if I is greater than J and I is less than the length of the whole array. And then we merge the two. Just take a look at the source, look at the code, and you see that's how it works. Alright, since we see what merging is and what we understand, and we understand what merging is, we can move forward to two-way merging. Two-way merging is basically merge sort, but we'll get into that. Let's say you have 4 arrays, A, B, and C, and D, and you want to merge them. You can merge them by doing it like this, comparing values of A to values of B, values of C to values of D. Here's the result of A. There is the comparison of A and B, the comparison of C and D. Then you merge it again. You merge these two arrays that have been merged already into this whole array. It's basically multi-step merging. Then another name for this is M-way merging. Sorry, M-way merging. Alright, there's again another way to do this, and by comparing A and B in one list, then you compare this list with C, then you merge this list with D. You can do it the other way around, you can do it for center elements. So you can define two-way merge sort as an iterative process using loops. So this whole thing is made possible by the virtue of loops. So given this array 9, 3, 7, 5, 6, 4, 8, 2, right? We assume each element is sorted. So basically we are assuming that 9 is an array, 3 is an array, 7 is an array, 5 is an array, 6 is an array, 4 is an array, 8 is an array, 2 is an array. We assume it's an array, and because it's the only value, the list is automatically sorted. So we're merging the lists. We use two-way merging. So we compare 9 with 3, 7 and 5, 6 with 4, 8 with 2, and then this is the first pass. The results are here. and then we compare these two results. Compare these two results, and then we compare these results to give us the sorted list. You know how merging works, so this is what happens. So now let us look at the time complexities. We know that these are 8 elements. There are 8 elements in this array. And in the first pass, there are also 8 elements. The second pass, there's still 8 elements. The third pass, there's still 8 elements that are being compared. Sorry, 8 elements, but they have been switched 2 times, have been merged. 2 elements have been merged. We've merged 2 times. So 1, 2. Here is again, we've merged 2 times. 1, 2. We have merged 2 times again. 1, 2. So it's n, n, and n. The n elements, right? And then we can basically say, because there were 2 merges here at each level, at each pass, we can express it as, we can express 2 as the base, right? We can express 2 as the base. There are 8 elements and there are 2. There's 2 merges happening, which give us 3 passes. And again, when we look here, there are 3 passes. Therefore, we can say the number of passes is log n. And the time complexity for two-way merge sort is big O n into log n. I hope you understand that, and let me give you time to absorb everything. All right. Now we are moving to merge sort. There's a difference between two-way merge sort and merge sort. Merge sort is made possible. There's a difference between two-way merge sort and merge sort. Merge sort is made possible, two-way merge sort, is made possible by loops, and merge sort is a recursive procedure using the divide and conquer method. Divide and conquer means you actually divide the problem into smaller chunks and solve the smaller chunks. Later, we combine the solved chunks into one big chunk. And recursion is a way of solving problems where a function calls itself to break the problem down into smaller, easier to solve parts. Alright, we're given the same array we had for the previous one, but this is how we can represent it using pseudocode, right? The algorithm merge sort, L is the first element here, and H is the last element. And it only continues if L is less than H. The midpoint is L plus H divided by 2. Here's the division point. We divide and conquer. And then the merge, we merge from the left side to the midpoint. Then once that's done, we go to the midpoint to the right side, and then we merge the whole element. Let's see how you're understanding these. This is the merge tree for the elements. So we're given 8 elements, 1 through 8, and we divide it by 2. There's elements 1 through 4, and there's elements 5 through 8. So we just go to the left side, we divide it again, 1 into 2, 3 into 4. And then it's up until we have one element. Then we come back to merge the elements. We come back to merge the elements here, then we merge it here, then go to the right side. We end up with one element, we merge them again, merge them here, and then once both sides have been merged, we merge them together at 7. So merging goes from 1, 2, 3, comes this side, 4, 5, 6, comes to the top, 7th, merge. Each level of merging is the value of n, the number of elements. Therefore, the time complexity for merge sorts recursively is still n theta to n log n, n into log n. All right. So using the numerical values, we used elements here We use the elements here, and now we're going to use the new actual numerical values. We're given this array. And again, it's the same procedure. We split them, we split them, we split them. These are just sorted. This is the final product. It's sorted. But basically, you can see that 3 is into 3, 5 is into 5, 7 into 7. We merged, we split them, we merged them. It's sorted, we merged them, they're sorted, we merged them, they're sorted. We split, we merged the values, we merged them again, and we sorted them. And we merge them again, and then now they're sorted on both sides. And we merge the two to give us the sorted array 2, 3, 4, 5, 6, 7, 8, 9. The time complexity is still the same. It's theta n into log n. All right, now we are going to look at the pros and cons of merge sort. Merge sort is efficient for large lists. Its recursions work better for linked lists, and it supports external sorting, meaning it because the array it's the sorted array is stored in a different array. It's in an empty array, different array. It's good for this. It is stable. The order of duplicates remains the same. The cons, it needs extra space for sorting because the results are sorted in a separate array, and it is slower for lists in the interval of n less than equal to 5. Slower than algorithms like bubble sort and insertion sort in this interval, but as it grows, it's more efficient and it's faster. It's not space efficient because it uses n for storage of the extra array and log n for recursion. The recursion is log n and storing the array is n. All right. This is a basic crash course to merge sort, and I hope you get everything you need to know about it. There's a GitHub repo. I've represented the code in Python, and you can do whatever you want with it. You can steal it and or do whatever. Thank you for your time. Peace. All right.